Okay, students, this session we are going to discuss with a new topic, and in the point of examination view, I am going to give the just important topics and going to overview, or I am going to brush up you, isn't it? Okay, what are alkynes? Alkynes means those are all the compounds. They are containing the C triple bond H or C triple bond C. The compounds containing C triple bond C are called as alkynes. Okay, so usually while nomenclature we are going to use by using the suffix YNE. Okay, alkynes. Okay, so basically we are going to consider these alkynes are linear molecules. Why we are going to classify this under linear molecules, and what is the bonding nature? Okay, here we can observe the sp hybridization with two unhybridized p orbital that overlaps to form a pi bonds. Okay, let us take a look. Okay, how the hybridization happens. Okay, so suppose this is the carbon atom, this is the pi bond, p orbital. This makes a carbon and sigma 1 pi bond. Okay, so here it is one more carbon atom. Okay, so you know that one, all the p orbitals, they are perpendicular to each other. For example, px, py and the pz, these three are the orbitals. They are perpendicular to each other. Okay, so in this case what happens, so the sigma bond is going to form by means of the carbon that containing the one p orbital. Okay, that forms a sigma bond between the carbon atom. Okay, and one more sigma bond by means of the carbon atom, two carbon atoms with the two hydrogen atoms. Okay, so this will form a sigma bond, that is a stronger bond. Okay, as the effective overlapping is there. Okay, here we can expect the effective overlapping because of the pi bonds. Okay, so the bond length is going to shorten compared to that of the alkanes. Okay, as well as alkenes. Okay, so because of the bonding in nature, effective overlapping we can expect. Okay, and what are these one? These two are the pi bonds, isn't it? Okay, so these pi bonds, they are mutually perpendicular to each other. Okay, and three bonds also, they are mutually perpendicular to each other. So that what it can form? Alkenes, we know that one, they are the fixed rotation. You cannot rotate the carbon double bond. Okay, why? Because of the rigid rotation that happens between the px and the py orbital. Okay, two pi bonds are there. Okay, here what is there? One more pi bond is there. That makes the carbon triple bond C further rigid. That is why the alkynes molecule, alkyne nature, okay, they are linear in nature. Okay, and what about the hybridization? So this is S, this is P, the sp hybridization. Okay, and the remaining two p orbitals which forms a pi bond. Okay, they are the weak bond, isn't it? Okay, so next, what are the consequences of this carbon triple bond C, and what are the types of alkynes? Okay, so when we are talking about the types of alkenes, basically we classified alkynes are into generally two types. Okay, so first one is the terminal alkyne. This is terminal alkyne. Okay, what about this terminal alkyne? Means the C triple bond C is present at the terminal of the carbon at the terminal of the compound, so that it contains a one acidic hydrogen. Okay, we can discuss it later. What is this acidic hydrogen? Okay, so and one more alkyne is, it is internal alkyne. This is internal alkyne. Okay, so what is the meaning of this internal alkynes? Okay, so this carbon triple bond C, it is stuck between the two alkyl groups or any other two aryl groups. Okay, so here what is the case? Okay, one of the carbon triple bond C, it is substituted with one R group. Okay, and the one more side is, it is simply a hydrogen. Okay, so these are the general classifications of the alkynes Okay, so and this is most important for our further discussion. Okay. Okay, so next one is acidity of the alkyne hydrogen. Okay, or it is also called as acetylenic hydrogen. Okay, so whenever a terminal, especially in case of the terminal alkene, okay, the carbon which is attached to a one hydrogen atom. Okay, sometimes these H may be replaced by the R group, okay, or sometimes it may be replaced by the any other simple atoms like hydrogen. Okay, then also it forms a one alkynyl hydrogen is there. Alkynyl hydrogen is there, that is called as acetylenic hydrogen. Okay, so what about the pKa values? Okay, what is this pKa value? pKa value indicates how much acidic it is. Okay, as the pKa value, which is always indicating the acidic nature of the compound. As the pKa value gets lesser and lesser, the compound is more basic in nature. Sorry, acidic in nature. For example, HCl, which is having the pKa value of -7. Okay, this -7 indicates it is more acidic in nature. Okay, when you are talking about the acetic acid, the pKa value is around 3. Okay, which one is the lowest value? -7 or 3? +3. Okay, so -7 value is the lowest value. That is why as the pKa value decreases, the acidity is going to increases. Okay, so here we have taken the ethylene, okay, acetylene, ethylene, and the ethane. Okay, so if you the hydrogens, okay, here it is attached to a C triple bond CH, here it is attached to a double bond CH, here it is attached to a single bond CH. Okay, so the acidity value is, it is 25. For an alkene compound it is 44, and for a alkane compound it is 50. Okay, so that is why it is very difficult to remove a proton from a ethane. Okay, so it does not show the acidic character. Okay, that is why it is not possible to easily remove a hydrogen or a proton from the alkane compounds. But what about this acetylenic hydrogen? This is, since it is acidic in nature, the pKa value is very less. Okay, by using a strong base, it is easy to remove the acetylenic hydrogen. Okay, that is the importance of this one. Okay, so what happens after the removal of the proton? Okay, HCl is there. Okay, on dissociation, what happens? It liberates the hydrogen, and this hydrogen give its proton to the another thing. Let us assume water as an example. HCl plus water. What happens? Okay, HCl plus water. What happens? H3O plus Cl minus. It is a strong acid. Okay, or you can say it is a acid. Okay, so after the hydration, after the donation of a proton, it becomes its conjugate base. Here water is a base which is accepting the proton from the acid. After the receiving a proton, it becomes a conjugate C. I am writing in short form, conjugate acid. Okay, so in this conjugate acid, a stronger acid, after the donation of proton, it becomes a weak base, isn't it? In the similar way, this acetylenic hydrogen is highly acidic in nature. Okay, because so a strong base is enough to remove this proton. Okay, but in case of the alkanes, it is very difficult. Even by using a strong base, we cannot pick up this hydrogen. Okay, suppose assume that you have removed a proton from this ethane, ethylene, acetylene. Then what happens? They, after removing the protons, they becomes their conjugate base, isn't it? Okay, if you consider this is a acid, after the removal of proton, after the donation of a proton to someone, what it becomes? So it becomes a base. Okay, here it is a yes, acidic in nature. Here it is acidic in nature. After donation of a proton, it becomes a very weak base, isn't it? Okay, what about in ethane? ethane, it is very highly difficult to remove a proton. Okay, that is why it is very weakly acidic in nature. But after removing a proton, then what it becomes? It becomes a stronger base. See, here I have written the order of the, after removal of proton, it becomes a conjugate base. Okay, so their order is this ethane CH3 CH4 minus is more acidic than the CH2 CH minus, than it is more basic than that of the acetylenic base. Okay, so this is called as, this is based on the acid base concept, or you can say conjugate acid base mechanism. Okay. Okay, so what is the summary of this thing? Okay, the summary is like this. Okay, it is very easy to remove a proton from the acetylenic hydrogen or from a terminal hydrogen. Okay, so after the removal of proton, it becomes a weak base. Okay, but a good nucleophile. Okay, so what are the consequences of this reaction? You can discuss it in on the next slide. Okay, so in this slide I have given a reaction. Okay, a compound that is a strong base, sodamide. I am reacting with this of the one terminal alkyne compound. Okay, what happens if you are going to add the strong base? Okay, I already said this is highly acidic in nature. Okay, so NaNH2 sodamide, it is being a strong base, it can easily pick a proton from this alkynyl hydrogen or acetylenic hydrogen to become a nucleophile. Okay, it is a very weak base but a good nucleophile, isn't it? Okay, so it is acidic in nature. Okay, what about their base? It is obviously, it is highly acidic, means their base is a weak base but a good nucleophile here. Okay, why it is a good nucleophile? Means the carbon containing the negative charge, isn't it? Okay, that is the thing. Okay, so then what it sodamide becomes? So NH2, which picks a proton to becomes a ammonia molecule. Okay, it will escape from the reaction mixture, of course. Okay, so then what happens? This acetylenic carbon ion, okay, so which can add to the any alkyl halide. Okay, usually a primary halide, in such a fashion that one. Okay, so this nucleophile which can comes and attach to this carbon atom of the alkyl halide. Okay, so because it contains the partial positive charge, halogens always carries in partial negative charge. Okay, when it attached to this alkyl halide, then what happens? The bromine is going to eliminate in the form of bromide ion, which leads to the formation of the one more carbon-carbon bond. Or we can say that one, it is by using the terminal alkenes, it is very easy to synthesize the carbon elongation is possible by this method. Okay, so then first, then next we can discuss the stereochemistry. Okay, suppose assume you have taken a terminal alkyne. Okay, to this you are adding the sodamide. Okay, so and then you are adding this one. Okay, then what happens? What is the product? Okay, or what is the stereochemistry of this product? Okay, so first what happens? The sodamide which deprotonates a acetylenic hydrogen, then what it becomes? So R, C, triple bond C. Yes. Okay, then it forms, which can attach to this carbon atom, and this bromide ion is going to eliminate, and this leads to the carbon molecule. This is the compound R dash hydrogen. Okay, so in this case easily we can explain the stereochemistry of this one. Okay, stereochemistry of this one. Okay, so if you observe this molecule, this is a primary halide which can undergo nucleophilic substitution reaction by SN2 mechanism, because SN2 mechanism is a single step reaction, isn't it? Okay, so after the deprotonation, the alkynyl carbon ion which can comes and attack from the backside plane. Okay, so that the elimination of bromine takes place. Okay, so to its front. Okay, so the backside attacking takes place from the front, the bromide is going to eliminate, so that's why we are going to call this one as SN2 mechanism. Okay, so what is the product of SN2 reaction? The product of SN2 reaction is inversion in configuration. Suppose assume that if this is primary halide, okay, if this primary halide, okay, it is a different. Suppose in the case of hydrogen, we have deuterium. Okay, what happens? This is a chiral carbon atom, isn't it? Why it is a chiral carbon atom? Because it contains four different groups. One is deuterium, one is hydrogen, and another one is any alkyl group, and another one is the halide. Okay, so suppose assume this is having a one particular configuration R. Okay, so then what is the product configuration? The product configuration is always ES becomes ES. Suppose this is deuterium. Okay, so why it is R is changing to S? Because it is forming the acetylenic carbon ion which attacks the primary halide from the backside attack, or you can call the acetylenic carbon ion which attacks to the primary halide by SN2 mechanism. The resultant of SN2 mechanism is inversion of configuration. Okay, so you will get the opposite compound, that is inversion of configuration is the stereochemistry. Yes, isn't it? Okay, so this is the one thing. Okay, so in the next slide we can discuss one more thing. Okay, suppose let's solve this problem. Okay, how will you synthesize 4-phenyl 2-butene by using the phenyl? Okay, by using this compound. Okay, so what is this compound? Okay, that is called as benzyl bromide. This compound is called as benzyl bromide. What is the problem? They have given the benzyl bromide. What we have to synthesize, that is 4-phenyl 2-butene. 4-phenyl so this is called as 4-phenyl 2-butene. How will you by using the benzyl bromide? How will you synthesize this one? Okay, so assume that. Okay, so here is the. Okay, so what is the product that you want? 4-phenyl 2-butene. Okay, so you want 2-butene. Okay, so you want to introduce 2-butene group. Here it is already one carbon atom is there. Okay, what you want to further introduce? So you have to introduce the further 3 carbon atoms. Okay, so what is the compound, or what is the starting material that we can choose? Okay, here I am writing one compound. Okay, so you just see, is it enough? Yes. Okay, so this is containing the one propane which is having the 3 carbon atoms. Okay, this 3 carbon atoms with one acetylenic hydrogen is there. Okay, so if you are going to add sodamide for this one, what happens? The removal of the one acidic hydrogen takes place, then which leads to the formation of this carbon ion. This carbon ion which goes and attack over this one, and which will eliminate the bromide ion. Okay, then what happens? The CH3 which is remaining as here only, the CH2 is comes here. Okay, then what about this one? Then this carbon atom which containing the 1 2 3 4. Okay, so then this carbon atom which makes a bond with this one. Yes, this is the bond. Okay, so this is the acetylenic hydrogen. Yes, this is the, I am giving in the star mark. This is one more acetylenic hydrogen. This is one more acetylenic hydrogen. This is CH3. Yes, this is CH3. Okay, so by this way it is possible to construct a carbon-carbon bonding compounds by using the terminal alkynes. Okay, so what you require? You require a strong base. Okay, after it becomes a nucleophile, if you are going to add any alkyl halide, okay, then you will get this compound, isn't it? Okay. Okay, so next one is the conversion of alkynes to alkenes. Okay, this is a very important topic, especially in terms of the alkynes. Okay, so why it is so important? Okay, so first we can generally discuss the reduction. Okay, so previous videos we have discussed that one, alkenes on reduction by using the nickel or platinum or palladium catalyst. What is the product? you will simply get the alkanes. Carbon-carbon is double bond, carbon-carbon double bond is reduced to the carbon-carbon single bond. Alkenes are converted to the alkanes. Okay, so what happens if you do with such a strong reducing catalyst such as platinum, palladium, nickel for the reduction of alkynes? Okay, here also you will get the same compound, that is alkynes are directly converted to the alkanes. Okay, if you take butane in presence of palladium, directly you will get alkanes.